Hi, good morning. Well, I was going to do this live, and I did attempt to do it live, but the internet seemed to be dropping out a lot. It does happen in hotels, so I unfortunately have to record this. So first of all, there's an apology, and then B, let's get on with it. All right, so hopefully second time round more successful. The first thing just to say, look, we do have the ZP Academy. It's got a couple of free courses on it. It will introduce you to electrochemistry. It's worth signing up. We do webinars. There's plenty of webinars. There's webinars next week on Julie, Sense It All platform, and we're also doing special webinars with kind of collaborators in places like India. We have been hiring from USN. USN is a sort of excellent university that's kind of near to us, and they run an Erasmus course, which is really a great course, and we get really elite people from there. We also have our ZP Developer Zone. This kind of webinar every week is about that. It's about supporting people, especially I would say more in academia than necessarily in industry. But we do support people in biosensing and electrochemistry. We do have workshops. So every, how do I say this? Every month we have a workshop either in the UK, in Norway, or both. We've got one in Norway on the 11th to 12th of September. I've just been booking my flights for it, so I know it's going to be going on. And we do have one in Coventry as well. That's next week, so it may be something like the 7th or 8th. I think it's the 8th of September. We do have a large conference running in Norway on the 13th and 14th. It's called the Scandinavia Sensor Summit. I'm really keen to get a lot of people along to it because it's really about measuring and sensing in the world, be it health or environmental, etc., to really improve outcomes for mankind. I think sensing and measurement is actually a force for good when done correctly or in the right applications. Improve somebody's health or improve somebody's environment. The Scandinavia Sensor Summit, this is a link to it. I will put this link underneath the video once I've uploaded it. Questions this week, flow cells for biosensors, phosphate sensors. I will cover phosphate sensors. Further questions on CGM. So we do get a lot of questions coming in on CGM. EIS experiments for teaching labs. It's a good question for us, how to do EIS teaching or how to do an experiment on EIS for teaching labs. Can I reuse SPs? Can I reuse screen-repeated electrodes? Also, OEM Solutions for dissolved oxygen and pH and gamma irradiation. And then making a CGM sensor, how to make a CGM sensor. So first of all, on the flow sensor side, we have been discussing CGM quite a bit of recent. So I just put these slides up there just to say, you know, honestly, today's the 31st of October. If you find our webinar on the 4th of October, you will find a lot of CGM. And I even think the week before that, we were doing a lot of CGM as well. So these webinars, if you go back in time, you will find a lot on CGM. Now, this particular person was interested in flow cells. So I just want to say, I've just put a couple of links here, and I'll upload this video and put the links underneath the video. But we do have a lot of, we do have flow cells for biosensors and bioreactors. So this is Andre. He's handling one of our flow cells in this particular video. And then later on, he actually puts the sensor into the flow cell, and then he's showing, you know, how to sort of drive it with a pump and how to do measurements on that flow cell. We do have this. We do have a question here about somebody's interested in phosphate sensing. So there's a part number. They're interested in particularly low phosphate level, well, not particularly low, but in lower phosphate levels. So the quick answer is we do have a phosphate sensor. We have not tested it at these low phosphate levels. And I'll say in a bit that you've got a sort of choice there as to whether you test it yourselves or you get us to test it for you at those levels. They would like to know the lifespan of the sensor, and the lifespan of a sensor really depends on where are you going to use it. Now, what I mean by that is people think that, you know, the emphasis is all on the sensor, but it's really the emphasis is all on the system. What is the system that you're going to do? What is the sample that you're going to be in? How is the sensor going to be in contact with the sample? These are all system level requirements. Are you going to do periodic calibrations on that sensor? These are all things that would actually, are you going to do any rinse steps on that sensor? These are all things that would influence the lifetime of a sensor. So people always ask us, and I always ask the question back, it's really part of the system. I suppose I've got some real data up for this. So I think we've tested it for like 1600 seconds, which is nowhere, that's 1600 seconds of continuous use. You know, that means that, you know, if you decided to expose the sensor morning and afternoon for 1 second each, if I did a quick calculation on that, I think that would give you 800 days worth of runtime. So it really depends on the use scenario. How do you get the signal out of the sensor? I will deal with that. And this is another one. Can you provide information on the accuracy and expected calibration drift of the sensor? I think the answer is this. You've got for every sensor in every application, you have to do this work. If we make a phosphate sensor, how it works in a saline solution, how it works in a saline solution such as blood, how it works in soil, these are ways that you have to do the work for it, or commission ZP to do that work as well. So we do have some data up on our website about the sensor, but I have done some calculations, and I'll run by those in a minute. But I can see here that the data that we put up here is, we've got nice stability, but it's over 1600 seconds. That's not necessarily for an environmental sample, and I could see these things being in position for years is ideally what people want. We have tested at 0.1 millimolar, 1 millimolar, 10 millimolar, and 100 millimolar. Now I did some calculations, and the range that they're wanting is, if we look at the 10 ppm range, then that is 0.000105 millimolar. So you're essentially 1,000 times below where we've tested. Will it work? I suspect it will, but actually we'd have to go in the lab and do it. So we do say to people, look, if you're interested in our sensors, including the phosphate sensor, we make them available on the website so people can essentially try and buy and try. And if they're not sure, they haven't got the setup for it, then we will also do that work as well if commissioned to do it. So it's an interesting application, and I think we stand a good chance. But there's gaps. What we have on the website is what we know, and whether it will work in a particular application is a different matter. Now, we do have a way of getting signals out of all of our sensors. Our sensors fall into categories of being amperometric, voltammetric, and potentiometric impedance sensors, but we have a single board that we can actually get all the signals out of. I have got a link to it, and so somebody says, well, how do I get the signal out of it, like a 0 to 5 volt signal? Well, there's two protocols on this board. There's I2C and there's UART. So any electronic engineer would be happy with those, I think. So that's how you would get the digital results out of the board. I'm just going to silence that. It's a bit loud, but I also want to say that phosphate kind of, for me, falls in alongside nitrate and potassium. So we are also quite capable of turning these sensors into, this is what I would call a spot test. It's a discrete measurement as opposed to a continuous measurement. I didn't put it in here actually, but we do have videos about how we can turn these sensors into continuous measurement sensors. So essentially we have a box, we have an app, we have a sensor, and in this video, which I've got a link to it here, Guyana takes the sample, puts it on the sensor, there's Bluetooth connection with the app, and we get a result for nitrate. So we're quite capable of taking these kind of sensors that are on the web store and actually uploading them. And what's quite nice about this as well is we actually show that we have a to-cloud solution. So you can sort of get the data out of a ZP sensor, either using that little board, which would be I2C or UART, or actually API, Application Program Interface. So hopefully that video and that link that I'll link to will be useful to you. As I say, especially on the company side of things, I think with academia, people have the kind of time and probably the breadth of tools and experience to sort of take our sensors and start working them into their applications. On the commercial side, people are in much more of a sort of hurry, need something a bit more robust, can't spend 3 years doing a PhD on it. In that case, we just say to people, we've got these services where we can do mini, micro projects, and we could do things that are much larger, but you probably sometimes need to engage us on those projects, especially on the commercial stuff. So the two big questions I see for this particular person is the range. Can we do the range that they require? And then the other, if I can call it a risk, is the drift in the, I say here drift in the sample, I should really say drift in the signal, my apologies. I was thinking of an S and I put in sample, but it's signal. So those are the two things which they've also identified, but I also agree with them that those would be the two things that I would be focusing in on. I say here further questions on CGM. So we do have a particularly active user at the moment. They've got some of our glucose sensors, so I appreciate that. They've got some questions. They've been testing with 5 to 10 microliters of solution. I'm really surprised, to be honest, which is great. Just out of interest, there's nothing wrong with small sample sizes. I've said it before, so I only say it because I know I repeat myself. A glucose strip, where they've kind of made this microfluidic chamber on top of the strip, will run on 300 nanoliters. There's nothing wrong with actually testing small volumes of solution. I'm just surprised that 5 microliters is enough to cover the electrodes. If you watch many of our videos when we're testing a bare sensor, when I say bare sensor, a sensor without microfluidics on it, we are definitely testing things like 30 to 50 microliters. So I'm surprised. I will talk about this in a little bit. He says here, can I clean the sensor and reuse it? Yes, just get some DI water, wash it down, let it dry. I don't want you to sort of rub it dry, just let it dry, and then you can store it. How many times can it be used for the second day also? Yeah, I mean, with the glucose sensors, wash them down, store them dry, so let them air dry, put them in the fridge, cover them up when you put them in the fridge, and they should be good to go the next day. You know, discard them when you think they're not working in anymore. But we do reuse our glucose sensors quite a bit. The thing about a glucose sensor is it's in contact with the solution, so they never really return to their original state. It's not like a thermometer where you can put it in there, measure the temperature, pull it out, wipe it down, it's good to go. No, sensors are not like that. You know, especially a glucose sensor, it's in very intimate contact with the sample. It does have an enzyme in it. It won't last forever. But we look after our glucose sensors and they last us, years. But I'm not going to absolutely promise on it, especially when somebody's on a learning curve with a glucose sensor. They'll do stuff that we would have not thought of. Not meaning to abuse a sensor, but it can happen. It takes a while to get a stable signal, or he says data, but stable signal. Yeah, it does take about, for us, 100 seconds sometimes to get a stable signal. Sometimes we allow it to stabilize for 500 seconds. I mean, the sensors that you have are intended for CGM, continuous glucose monitoring. So these kind of settling times are really sort of acceptable. If you put an Abbott Libre Freestyle 2 or 3 on your arm, which is a leading CGM on the market, then those will take an hour to settle before they will actually start giving you signals. How does the sensor sense glucose? Yeah, sure, I'll do that. So first of all, about your volume as well. We want to cover all the electrodes, so make sure that these very small volumes that you're using are actually covering all these electrodes. We tend to use 30 to 50 microliters. If you're getting away with 5 and 15, good to you. I'm surprised, but good for you. In terms of this glucose sensor, how's it actually working? Actually, come to one of our workshops. We do get into this in a lot more detail, but I'll be quick here. We have an enzyme layer on it. We have a barrier layer on it. By the way, somebody else is trying to buy. You can also buy these solutions from us as well. That'll be in one of the points later on. So we have an enzyme layer. We have a barrier layer. We have the glucose. The glucose is in the solution. Not all of the glucose gets the enzyme layer because of that barrier layer, but we want the barrier layer there in part to give us what we call clinical range, and it does actually help with robustness and lifetime as well. Essentially, the thicker the barrier layer, the smaller the signal, but the more robust the sensor is, but also slower it is to respond. So life is a compromise, and so we put a barrier layer on there. I think somebody was actually asking whether they needed to put a barrier layer on at all. So the glucose is diffusing to the enzyme. It reacts with the enzyme. the enzyme receives electrons from the glucose, and the glucose becomes glucolactone. So the glucose is essentially oxidized at this point. You'll see sometimes people write gluconic acid, and that's because glucolactone hydrolyzes naturally in water to form gluconic acid. But the first product is glucolactone. And in order for that transformation to take place, it's the enzyme that receives electrons. The enzyme reacts with oxygen. Oxygen is a natural mediator for it because the enzyme is an oxidase. Oxidase is, the hint is in the name. It likes to react with oxygen. It forms hydrogen peroxide, and the hydrogen peroxide is what diffuses to the electrode. And if you apply 650 millivolts, which is something that we've done enough, we've done things like cyclovoltammetry to allow us to understand that this is the right potential when doing amperometry. And I would do, if you come to one of our workshops, we really talk about amperometry versus voltammetry in that workshop. That oxidized hydroperoxide gives us electrons and recycles the oxygen. So that is a 4-minute, I'm sure it's a bit shorter than that, of how a glucose sensor, and at least the ones that you got, your generation 1 glucose sensors, how they're working. Question number 4 is about EIS in the teaching lab. So it's a nice question. The gentleman who asked this question, by the way, he builds his own potentiostats. He's one of the there's a few open source potentiostats out there, and so he's one of the developers of that. So I have great respect for him. We do use a lot of EIS in making electrochemical biosensors, but these are not, when we do these kind of experiments, they're beautiful, that we put antibodies on the surface and we attach antigens to those antibodies, and the signals are sort of changing. The more antigen we put in there, the increase in the impedance of the surface and the increase of the capacitance of the surface, and we see that in the change in the Nyquist plot. So we do this kind of work, but this is, I would say, too complicated for a teaching lab. What we would suggest is we have something called the hypervalue carbon electrodes, hypervalue screen printed carbon electrodes. I always suggest these because we make them in such high volume. They're good, high quality, and low cost. In fact, I link to it here. When I say that, you can buy a sheet of these. They're all perforated, so you can just spring them out. And a sheet is 250 euros for 300. So it's perfect actually for teaching. I mentioned it earlier on, but put solution volume on here. I'll make the comment here. Put 50 microliters on the end of it. Now the test solutions are, I would do sort of essentially 3 experiments. One of them in just 1 molar NaCl. One of them in 1 molar NaCl with 1 millimolar sodium ferrocyanide, and then in 1 molar NaCl with 10 millimolar sodium ferrocyanide. I should have said ferrocyanide to make sure I get the right oxidation state. This is the kind of reduced form of, it's not ferricyanide, it's the reduced form of ferrocyanide. The instrument, I would suggest that you put a DC offset of 100 millivolts, because I'm really trying to do what's called a Faradaic EIS experiment, because I've got ferrocyanide in there, so I put 100 millivolts in there. Ferrocyanide is going to oxidize, so this is Faradaic as opposed to non-Faradaic. I put an AC amplitude on top of that DC offset of 10 millivolts, and I would try a frequency range of 1000 hertz to 100 kilohertz. You don't really need to go beyond 100 kilohertz, but you may want to kind of come down to 100 hertz. The only reason I'm not suggesting 1 hertz is because it can be a very slow experiment. I'm thinking about, you've got a certain amount of time in order to get this teaching lab done. So I'm sort of giving you a suggestion of some starting parameters here. You can tune these up a bit, but this would be my starting parameters. I mean, the chemistry model, what I think is going on here is that what should be happening is that you have ferrocyanide that at 100 millivolts, some of it's oxidizing to ferricyanide, and we have a kind of an equivalent circuit here. I could have really put in what's called the Warburg element. This guy builds potentiostats. He knows what the Warburg element is, but I'm really hoping that the charge transfer resistance is going to be proportional to the amount of ferrocyanide. Essentially, the more ferrocyanide there is, the easier it is to produce this current, and therefore the charge transfer resistance should go down. So the solution resistance should be fairly consistent. Well, it will be consistent between those 3 solutions. because you didn't really affect any kind of ionic conductivity. Between the 3 solutions, it's all dominated by the 1 molar NaCl. That charge transfer resistance, I suspect, should be the charge transfer resistance should be highest for the 1 molar NaCl and the lowest for the 10 millimolar ferrocyanide. You may have a bit of double layer capacitance, and then obviously you can, I don't suggest you go on a 1 frequency. I suggested 1000 hertz, but when you're playing with this, you may want to go down at lower frequencies, but the low frequencies will obviously go through this part of the circuit. Not obviously, but we would explain this in one of our workshops. The high frequency, I'm not suggesting 1 megahertz, I'm suggesting 100 kilohertz. We'll probably go through more of the capacitance circuit, part of the circuit, and then the 1 kilohertz, something intermediate like 1 kilohertz would go through both parts of the circuit. I've referenced this because I did take this figure from a paper. I have referenced it, so you can find that original paper. But it just illustrated what I was expecting in some ways, that as the ferrocyanide concentration increases, I suspect that your Nyquist plots, your radius, because the charge transfer resistance is going down, the Nyquist plots will actually get, at least that radius of that semicircle will get smaller as the concentration actually increases. But give it a go. If you've got results, if you give it a go and you've got results, share them with me and I'll try and talk through what I think I'm seeing. If you don't have any equipment, you don't build potentiostats, this is just a series of equipment to actually do, let's say, those kind of experiments, connectors, solutions, the electrodes that I'm recommended. So it's sort of there. And if you've got any questions, we're pretty responsive, so reach out to us. Reusing screen printed electrodes. Can I reuse screen printed electrodes? You can reuse screen printed electrodes, but I would say this: if you're using a glassy carbon electrode, this is a sort of pyrolytic carbon, sometimes people call it, but I used to use glassy carbon electrodes, and you would polish it every time you used it. So there's really no difference with screen printed electrodes. The problem is with screen printed electrodes, you can't really polish them. So can I reuse screen printed electrodes? Yeah, you can do what you want, but with time, those surfaces are going to foul up. And most of the time, if we're using, as I said, a carbon electrode that's been, it's glassy carbon, we would polish it. You don't have that option. So you can do it. You can reuse them. It's up to you. But would we do it? Would we do it as EP? We absolutely would not do it. It's just that simple. Because we can't really clean the surface. We can't ensure that the surface is the same the second time or the third time we reuse it. I would say it's a bad idea, actually. Because they want to kind of mobilize an enzyme on top of it and then wash it off and reuse that sensor. Immobilizing an enzyme on top of a sensor is often involves some sort of cross-linking and some sort of attachment to the electrodes. You are going to remove parts of the electrode when you try to remove the enzyme. So would we do it at ZP? We absolutely would not do it at ZP. We're not going to have good quality data. We're going to be interpreting electrodes that have a history effect on them, so it's not going to be good for us. They were asking here whether if they load more enzyme onto a sensor, will they essentially have more activity? It is. If you don't put enough enzyme on a sensor, you will essentially not have much linear range. So the answer is yes. You do want to load up that sensor with enzyme. And you probably, if your target is a small molecule like glucose and lactate, you do want an excess of enzyme so that it's not a rate limiting step. But you can't just keep on loading enzyme up. It's not a linear return on investment. There's basically a plateau at some point where you can't get any more enzyme on and it's just going to start delaminating. But the simple answer to your question is yes, the more enzyme you put on there, then the higher the enzyme activity on the sensor, and that's probably a good thing. But there's a point at which you can't put any more enzyme on there and you just start running into new problems. So it's a fine balance. So I suppose with ZP, when we make our glucose sensors, is they're not just throw some enzyme on there. No, actually we've come to this through calculation and through experience. Yeah, and the reason that we tell people not to reuse electrodes is I don't like the fact that there's a carbon footprint associated with these electrodes. will we solve this and make these kind of biodegradable? Yes, we will. At the moment, they are polymer. So I do understand that, but we would never reuse our electrodes. I mean, this is why we try to make them low cost so people can actually not have to reuse them, because every time you use a screen printed electrode, you're building up a history on that electrode, and you can't just wash it off. And yes, this is just to reiterate on when I was giving that kind of talk earlier on about how a glucose sensor works. And if you haven't seen that part, go up to the top. I suppose I didn't say in that is that we put enough enzyme on there that the thing that's really limiting the signal is glucose. So if you've got not enough enzyme, where you try to test your clinical range, you find out that the signal stops increasing with concentration, and it could be enzyme limited. At which point then you could either increase the amount of enzyme or increase what's called the barrier layer. Now, that actually makes good sense, because question number 7 is about building a glucose sensor. So wait on for number 7. Question number 6, somebody wants to measure pH and dissolved oxygen in cell culture. OEM means original equipment manufacturer. So I often use this term when thinking about other companies who want to use our technology. So we do have a set of electronics, and we do have the actual sensors. So this is this is the pH sensor. This is the oxygen sensor. This is the electronics that we support. So essentially, we won't support any other electronics. And people can get the signal out of this and put it into their product by using an I2C protocol or using a UART protocol. Question number 7, making a CGM, making a continuous glucose monitoring sensor. We do have workshops on this. As I mentioned at the beginning, 11th and 12th of September. I know this will be happening because I've booked my tickets. I'll be giving it. Definitely come along to one of these, or reach out to us, because we do hold these every month. And in there, we teach people, look, here's a platinum electrode. We're going to put some enzyme onto that surface, let it cure, then put a barrier layer on it, let it cure. And I just want to point out that we actually do have these solutions. I also do have the electrodes that we use as well. So apologies, this didn't go live. Just the internet dropped out, so my apologies for that. ZP does have flow cells for biosensors. I'll put a link. Phosphate sensor, you've really got, and you recognize it yourself, 2 gaps. One of them, your range of interest is below what we've tested, so it has to be tested. Buy and try yourself, or give it back to ZP and we'll do it as a program. But then there's, I think, so I'm not so worried about that concentration. I'm actually more worried about the long-term stability, and it's long-term stability is something you can deal with by the total system. Do not think of sensors in isolation. Sensors are part of the total engineering solution. So if it's in the context of the total engineering solution, you can have years, but it's within the context of the total engineering solution, not just will that sensor do it. Further questions on CGM. Appreciate these questions. I'm really surprised you're getting away with such small volumes, but fundamentally, you should be able to. It's just covering all the electrodes. EIS experiment for teaching labs. I've described some starting conditions, and I've described some solutions. I think that will work for you. To be honest with you, can I reuse screen printed electrodes? I sound say yes, because you are able to do what you want. Would we do it at ZP? Could be another question, and the answer at ZP we wouldn't. OEM Solutions for people, we do have electronics and sensors. If you're really making a product, then I think your starting point, especially if you're very keen on doing all the electronics yourselves, that single purpose biosensor circuit and our sensors is a good start. Making a CGM, I just very quickly shot through making a CGM solution this morning. Okay, I just want to say thank you very much. Apologies that it didn't go live, but the internet was letting me down here. Okay, thanks very much.